Howdy, welcome to Elementary Statistics. I am Lance Curtis. This is the lecture for Section 8.2, Testing a Claim About a Proportion. Here in this lecture, we're going to talk about hypothesis testing as it applies to proportions. First, we'll go over some requirements that need to be satisfied because our methodology is based on certain assumptions which need to be satisfied for our methodology to be used. Then we'll get into the nitty-gritty of the test statistic, decision methods, the hypothesis test. We'll talk about different methods for making our conclusion of whether to reject or fail to reject H0. There's the p-value method, the critical value method, the confidence interval method, and what's called the exact method of hypothesis testing. So let's get into it. So in this section, we're going to examine different procedures for testing a hypothesis or claim made about a population proportion. We'll use the p-value, the critical value, and confidence intervals to perform hypothesis testing. We'll also examine two common methods for testing a claim about a population proportion. Many of the methods that we're going to be using assume a normal distribution as an approximation for the binomial distribution. However, there's a more exact method based on using the binomial probability distribution directly. We'll get into all of that in this lecture. First, let's talk about some requirements that need to be satisfied. So we have three requirements that must be met when testing claims about population proportions. The first is that the sample observations are a simple random sample. This is a pretty common assumption made in all of our different hypothesis testing methods. Second, we must make sure that the conditions for a binomial distribution are satisfied. That's because many of our methods assume that they use the normal distribution as an approximation for the binomial. On that point, the third requirement that must be met is that we have to have at least 5 failures and 5 successes. This allows us to use the normal distribution to approximate the binomial distribution. Note that P here is the assumed proportion in the population and not the sample proportion. Remember that the sample proportion is symbolized by P hat. So little p is the population proportion, whereas P hat is the sample proportion. Let's review the test statistic. We went over this in the last lecture, but let's just go over each part of the test statistic to make sure that we understand what it is that's going in to calculating the z-score for our test statistic. So first we have z, which is the test statistic. The test statistic itself is a z-score. Next we have p hat, which is the sample proportion. So we have a certain random variable x divided by the sample size n. Next we have little p, which for purposes of calculating the test statistic is the population proportion. Notice that q is the complement of p. So q is going to be 1 minus p. And then of course n is our sample size. There are basically a couple of different ways that we can decide our hypothesis test. One way is to compare the test statistic with the critical value. Another way is to compare the p-value with the significance level alpha. So notice we're comparing apples with apples. The test statistic and the critical value are both horizontal values. They're horizontal axis values for your distribution. So you can compare a horizontal axis value with another horizontal axis value. Or the p-value and the significance level alpha are each areas under the curve. So here we're comparing one area with another. Either way we go, if we're inside the rejection region, which is the critical region, then we can reject H0. Otherwise, if we're outside the critical region, we fail to reject H0. For two-tailed hypothesis tests, there's a third method that we can use, and that is to construct a confidence interval at the 1 minus alpha confidence level. We'll get into how to do this. We know how to make the confidence interval, but how to apply the confidence interval to a hypothesis test is what we'll get into later on in this lecture. Whatever method we use, we have to remember that when testing claims about a population proportion, using the test statistic or the p-value are equivalent. They're going to give us the same result since we both use the same standard deviation based on the claim proportion p. However, the confidence interval method uses an estimated standard deviation based on the sample proportion p hat. Consequently, the confidence interval could yield a different conclusion than the test statistic or the p-value. Therefore, the best practice is to use a confidence interval to estimate a population proportion, but then use the test statistic or the p-value for your hypothesis test about the claim of a population proportion. Let's look at an example involving antivirus programs. Based on information from the National Cybersecurity Alliance, 93% of computer owners believe they have antivirus programs installed on their computers. In a random sample of 400 scanned computers, it is found that 380 of them, or 95%, actually have antivirus software programs. Use the sample data from the scanned computers to test the claim that 93% of computers have antivirus software. Okay, so the first thing we want to do is check to make sure that our requirements are met. So the first requirement, are the sample observations a simple random sample? And we answer yes, they are simple random sample. Next, the conditions for the binomial distribution. They're satisfied. And we see that we have at least 5 successes and at least 5 failures. Therefore, we have the requirements met for using our methodology, and we can go forward with applying it to this particular problem. So, the original claim that 93% of computers have antivirus software can be expressed in symbolic form as p equals 0.93. So there's our claim in symbolic form. Now we write out our null hypothesis. Remember, equality always goes with the null hypothesis by definition. Therefore, p equals 0.93 is our null hypothesis. Since this was also the claim that we're making, the alternative hypothesis has to take the not equal sign, which is the complement to the equal sign which belongs with the null hypothesis. So our alternative hypothesis will be p is not equal to 0.93. Since the alternative hypothesis is using the not equal sign, what type of hypothesis test do we have? Is it one-tailed or two-tailed? I hope you said two-tailed, because that's what the not equal sign indicates. We have a two-tailed hypothesis test. So half of our critical region will be on the left side of our distribution, and half will be on the right. For the significance level, let's select alpha equals 5%. This is the most commonly used level for significance when we're choosing a value for alpha. So let's just go ahead and use that value. The sample statistic relative to hypothesis testing of population proportions is p hat, the sample proportion. Remember, the sample proportions are unbiased estimators. They target the population proportions, and so this makes this the relative sample statistic for testing population proportions. We can calculate our test statistic by hand if we use the formula for calculating the z-score for hypothesis testing of population proportions. And you can see the math here coming out to a z-score of 1.57. This is our test statistic. Alternatively, we can simply take the information they gave us about the sample and calculate the test statistic using StatCrunch. Once we have our test statistic, we can compare it with the critical value. We can also use the p-value method. To use the p-value method, we recognize that we have a two-tailed hypothesis test with a test statistic of z equals 1.57. So now we can actually go into the normal calculator in StatCrunch, put our z-score into the calculator and calculate the area which corresponds with the p-value. Remember, the test statistic is that horizontal axis value which provides the boundary for the area under the curve that represents the p-value. Since this is a two-tailed test, we're going to have twice the area under the curve for the one-tailed test. So we take this area, which is 0.0582, and we're going to multiply it by 2 to give us the two-tailed test. That gives us 0.1164. This then is our p-value. Alternatively, we could take the area in between two tails using the between option for our normal calculator. If we do that and put in both the positive and negative z-scores for our test statistic here down below into our calculator, the area that comes out will be the area in between the tails. So we're going to have to take the complement of that area in order to get the area in the tails. When we do that, as you can see here, the area in between the tails, 0.8836. We subtract that from 1 to give us the tails, and lo and behold, we get the same number, 0.1164, that we got previously. So whichever way you decide to do it, you're going to come out with the same answer. So we now compare the p-value with our significance level. Because 0.1164, our p-value, is greater than 0.05, which is our alpha, we are outside the critical region, and therefore we fail to reject H0. If we use the critical value to make the conclusion for our hypothesis test, again we have a two-tailed hypothesis test with a test statistic z equals 1.57. Because we have a two-tailed test, we can go into StatCrunch using our normal calculator, and using the between option, we get the area in between the two tails. Remember, we have a two-tailed test. We put in 0.95 for the area because we're looking for the critical values. Why are we putting in 0.95? Well, because the area in the tails is equal to alpha, and we set alpha equal to 5%. So the area in between the tails, which is what the calculator in StatCrunch is calculating, has to be the complement to alpha, and therefore we take 1 minus 0.05 to get 0.95 that we stick in here into our calculator in StatCrunch. Press compute, and out comes our critical values. Negative 1.96 is the boundary for the tail on the left. 1.96 is the boundary for the tail on the right. Notice that our test statistic lies outside the critical region. Our test statistic is 1.57, which shows up right here. However, our critical values of plus or minus 1.96 form this region here in the middle of our distribution. The rejection region are the tails of our distribution. The test statistic is not in the tails, but it's in that central region where we failed to reject H0 because we're outside the critical region. Therefore, we fail to reject H0 because our test statistic is in between those two critical values. It's outside the critical region. We can use a confidence interval method for a two-tailed test on population proportions. So, testing the claim that p equals 0.93 at the 5% significance level for alpha, that means 1 minus alpha gives us a confidence level of 95%. So we calculate our margin of error just as we would previously. Here's the formula. We get our z-score, alpha over 2, and then multiply it by the square root of p hat q hat over n. So we put our numbers in. We've already calculated our critical score. This is the z-score that we put in for the margin of error. It's the same number, 1.96. P hat is the sample proportion, which we're testing at the 95% confidence level. So therefore, q hat has to be 5%, and our sample size was 400. punch this out on the calculator, and we get 0.021. Now we have the general form for a confidence interval. We apply what we know, so 0.95 minus 0.021, 0.95 plus 0.021, and we get the upper and lower limits of 0.929 to 0.971. Now, because our 95% confidence interval contains the claimed population proportion of 93%, we accept the claim, or in other words, we're rejecting H0. Note this is a different conclusion from that produced with either the p-value or the critical value. Using either of those two methods, we fail to reject H0. That's why best practice is use your confidence interval to make an estimate on the population parameter. Then use the p-value or the critical value method for a hypothesis test on a claim made about the population parameter. So, from here we would conclude there is not sufficient evidence to warrant the claim that 93% of computer owners have antivirus software. This is based on the p-value and critical value methods, not on the confidence interval. Again, best practice is use the confidence interval to estimate the parameter, but then test a claim about the parameter with either the p-value or the critical value method of hypothesis testing. There's some things to know about using StatCrunch for proportion hypothesis testing. For one, most of all your homework problems are going to have they're pretty streamlined. So if you just use a single option in StatCrunch, it will provide most of what you need. Go to Stat, Proportion Stats, one sample with summary. If you go here, you'll get your options window that shows up. You can put in your information in the options window, press compute, and you'll get most of the information that you need most of the time. So just stick with this one option and you'll be good to go. Now, we've talked about this before in class, but for those of you who may not know, you don't have to go through these menu options in StatCrunch for every single problem you do. It goes much quicker if you just go to the results window that you had for the last problem you worked, and then up at the Options tab in the upper left-hand corner, press that Options tab and you'll get a drop-down menu. When you select Edit, it will take you back to this Options window where you can then put in new values for your new problem, press Compute, and you can get a new results window with that new input values. So you don't have to go back to these menu options time after time after time and open up all of these separate windows. You can just use the one. It's actually makes the work go a little bit quicker. Let's look at an example problem to illustrate hypothesis testing on population proportions. In a KRC research poll, 1,002 adults were asked if they felt vulnerable to identity theft, and 531 of them responded yes. Answer the following questions with respect to the claim that the majority of all adults feel vulnerable to identity theft. First, what are our hypotheses? Second, what is the test statistic? Third, what is the p-value? 4, use a 5% significance level to decide whether to reject the null hypothesis. And last, what do you conclude from the hypothesis test? Let's look at each one of these questions individually. So our first question is, what are our hypotheses? Well, first we want to get the claim in symbolic form. So think of the claim that's being made. What is the claim that's being made? If you look at the information above, you see where it says claim, the majority of all adults feel vulnerable to identity theft. So that means the majority feel vulnerable to identity theft, which translates into P is greater than 0.5. Greater than 1/2 is a majority, so that's just going to be greater than 0.5. So there's a symbolic form of our claim. Now we can actually make the null hypothesis. Remember, by definition, it is a statement of equality. So we're going to say for the null hypothesis that P equals 0.50. Next, we're going to make our alternative hypothesis, And in this case, it will directly reflect the claim because we have a one-tailed test. So P is greater than 0.5, forms our alternative hypotheses. Note, the inequality sign in H1 matches our claim and says that we have a right-tailed test. This will become important later when we're drawing our final conclusions and stating them in non-technical language. Next questions we had. Second question was, what is the test statistic? Well, to calculate the test statistic, we're going to go to StatCrunch, go to Stat, Proportion Stats, one sample with summary, enter our information into the options window. So we have 531 people who responded yes out of a total of 1,002. And then the default option is the hypothesis test, so that radio button doesn't need to be changed. The claim value is 0.5, and we're going to put the greater than sign for our alternative hypothesis. Once we've made those inputs, we can go down to the bottom and press compute. And out pops this result window, and we can read our test statistic right off the result window. The test statistic will always be the next to last value in your results window. So it doesn't matter whether it's a z-score, a t-score, a chi-square score, it does not matter. Your test statistic will be the second to last value listed in the results window. The third question is, what is the p-value? And you can get that from looking at the results window. It's always the last value there in the window. So the last value is the p-value. The next to last value is the test statistic. Fourth question asked us to decide whether to reject the null hypothesis. Remember, if we're outside the critical region, we fail to reject H0. If we're inside the critical region, we're going to reject H0. So if we're using the p-value method, which is the one that's most commonly used because it's the easiest one to use, then we're going to look for see if p-value is greater than alpha. We have an area that's larger than our critical region, therefore it can't fit inside the critical region, which means we're outside the critical region, and so we fail to reject H0. However, if our p-value is less than or equal to alpha, we can fit the area for the p-value inside the critical region. Therefore, because we're inside the critical region, we reject H0. Here's our results window. Looking back at the p-value, we see we have a p-value of 0.029. This is less than 0.05. Therefore, we are inside the critical region and we reject H0. Alternatively, we can use the test statistic to evaluate. The test statistic in this case, 1.895, is greater than the critical value of 1.645. Where does the value of 1.645 come from? Well, it comes from our normal calculator in StatCrunch. So we put in our alpha level of 0.05, and then the critical value is that horizontal value which provides the boundary for that critical region. This then is our critical value, 1.645. When we compare with the test statistic, notice the test statistic is actually to the right, 1.895. So it's inside the critical region. That's the region of rejection, and therefore we can reject the null hypothesis. The last question asks us, what do you conclude from the hypothesis test? We're given 4 different options for writing out our conclusion. If you read each of these answer options carefully, you will notice that they are almost identical, with 2 major exceptions. One is there is or there is not sufficient evidence, and the second is you're either warranting rejection of the claim or you're supporting the claim. Because we have a one-tailed test, the inequality signs for our claim match those for our alternative hypothesis. And because of this, we're going to look for supporting the claim and not warranting rejection of the claim. If we had a two-tailed test, then we would look for warranting rejection of the claim. but we have a one-tailed test, therefore we're looking for supporting the claim. That means answer options A and D we can eliminate right off the bat. So the question is there or is there not sufficient evidence to support the claim? Well, did we reject H0 or fail to reject H0? We rejected H0, and therefore the correct answer is C. There is sufficient evidence to support the claim that the majority of adults feel vulnerable to identity theft. So, when your alternative hypothesis directly reflects the claim behind your test, you have a one-tailed hypothesis test, you're always going to conclude that you either have sufficient evidence to support the claim or you do not have sufficient evidence to support the claim. You're either rejecting H0 or failing to reject H0. That says whether or not you have sufficient evidence or do not have sufficient evidence, respectively. Rejection of the claim doesn't enter consideration when H1 directly reflects the claim. That's for a two-tailed test. I mentioned before there's an exact method of hypothesis testing. So the methods we have examined use the normal distribution to approximate the binomial distribution. We can produce more exact results by discarding the approximation and going directly to the binomial distribution. Hence, this is called the exact method. Now, because we're not approximating the binomial distribution with the normal distribution, we don't need to check to make sure that we have at least 5 failures and 5 successes. That's a requirement for using the normal distribution to approximate the binomial distribution. Because we're using the binomial distribution directly, we can just not worry about that assumption. So it doesn't matter whether we have that requirement met or not, because it's not really a requirement if we're using the binomial distribution correctly. So for a left-tailed test, the p-value is going to be the probability of getting X or fewer successes among n trials. For a right-tailed test, the p-value will be the probability of getting X or more successes among n trials. And for a two-tailed test, we have to compare our sample proportion with our population proportion. So if our sample proportion is greater than our population proportion, then the p-value will be twice the probability of getting X or more successes. However, if our sample proportion is less than the population proportion, then p-value is going to be equal to twice the probability of getting X or fewer successes. Let's look at an example problem to demonstrate. Going back to our gender selection example that we saw in the previous lecture. However, this time we're using this method of gender selection with only 10 randomly selected couples as opposed to 100. So of the 10 randomly selected couples that are treated with the gender selection method, 9 of the babies born are girls. So we've got 9 girls and 1 boy. So we use the 5% significance level to test the claim that with this method, the probability of having a baby girl is greater than 75%. So the first thing we have to do is recognize what are our null and alternative hypotheses. So here we have the null hypothesis, p equals 0.75, by definition, the statement of equality. And then from the problem statement, we're testing the claim that the probability of having a baby girl is greater than 0.75. So p greater than 0.75 becomes our alternative hypothesis. Now, this is a right-tailed test. We're using greater than as our inequality sign for our alternative hypothesis. It's like an arrowhead pointing in the direction of the critical region. So greater than pointing to the right, so that means we have the critical region on the right tail of our distribution, hence we have a right-tailed test. So the probability of getting 9 or more successes among n trials will be our p-value. We calculate the p-value, then compare it with the significance level, and then we can make our conclusion for our hypothesis test. So, using the binomial calculator, because we're using the exact method uses the binomial calculator. We put in our value for n, which is our sample size. We have 10 babies in our sample, our proportion for the populations, our probability of success, which is going to be 0.75. That's the value from the claim. And then our p-value is going to be the probability of getting 9 or more successes. Why 9 or more among the 10 trials? Because 9 of the babies were girls. So we take that information and that comes in to give us the area under the curve, which is 0.244. So this area on the right side, see how it's shaded in red? This is going to be the right tail. That's our critical region, and that's going to form. That's going to be our p-value then that we compare with our significance level alpha. So 0.244 is what we compare with alpha. Because 0.244 is greater than 0.05, we are outside the critical region, and therefore we fail to reject H0. So there is not sufficient evidence to support the claim that the probability of having a girl with this gender selection method is greater than 75%. That brings us to the end of this lecture. If you have any questions, be sure to ask. Otherwise, I will see you in class or the next video. Thanks for watching.